Hello everyone. Before we begin, if you can all please confirm that you can hear me and see the slides clearly by just typing in yes in the chat window. I'll check it from there. I see many yeses coming up. Okay, so please feel free to introduce yourself, your name, your position and company at which country you belong to. It's great to see an international audience of people from all the industries and backgrounds. Okay, great. So I welcome you all to today's webinar, which is the implementation of API RP2 SIM based SIMs for offshore structures. My name is Sayeda Samia Aves, and I am the lead software engineer at Velosi. For the next 2 hours, it will be our pleasure to host this webinar for you. We would like to thank you all for joining in, and we hope that by the end of this webinar, you will have gain good knowledge about the subject matter. So as some of you may know that this is our 56th webinar in a series of technical webinars we are conducting. As a practice, we conduct one webinar every second Sunday. You can follow us on LinkedIn and make sure to check our website to stay tuned to the latest updates. Furthermore, you can also subscribe to our Velosi channel on YouTube to view these webinars on the YouTube videos. So today we have quite an experienced panel of speakers. I am with my colleagues, Mr. Ijazul Karim Rao, who is the Managing Director, Principal Integrity and Safety Consultant, Mr. Anthony James Williams, who is the General Manager, Mr. Imran Saeed, who is the Manager of our BI Department. During this webinar, we encourage you all to keep asking questions in order to clear any kind of doubts that may arise with time. This will not only help you, but it can also help many others who can usually have the same kind of doubts. You can type in your queries in the Q&A window, and you will either receive a reply in the Q&A window itself, or we'll answer it live for you. We'll try to answer as many questions as possible during this session. Also, we will have a detailed Q&A session at the end after the completion of this topic. Please accept our apologies if your question is not addressed due to the high volume of questions that we usually receive. In this given limited time, we have to be selective. Also, we will be issuing a participation certificates to all those who have attended at least 80% of this webinar and have participated in the discussions through Q&A. Since this is quite a technical subject, and today we will be touching key theoretical and practical aspects of implementation of API RP2 SIM based SIMs for offshore structures. In this limited time of 2 hours, we request you all to follow along with us and keep asking questions to help us in making it this as engaging as possible. Before we begin, although most of us are in the comfort of our home, we should be aware of emergency exits. Due to the current COVID-19 situation and its emerging variants, we should be more careful, keep a safe distance, and in general, take care of ourselves and of those around us. So now I'll hand it over to Mr. Ijazul Karim Rao, who will start with today's topic. Thank you.
Assalamu alaikum and good day, everyone. Today's topic is basically we will be focusing on SIMS, Structural Integrity Management System, and that would be specific to offshore because the onshore structures are also part of SIMS, but technically the case studies regarding offshore. However, the concept is applicable both for onshore and offshore site. Like just a topic point of view, what is asset integrity by definition? It covers 3 elements: design integrity, technical integrity, and operational integrity. As a basic definition of asset integrity is a continuous process of knowledge and experience applied throughout the life cycle of an asset to manage the risk of failure and events in design, construction, and during the operational phase of the assets. In design integrity means assure design for a safe operations. Technical integrity means keep it in or like make sure there are processes of proper inspection and maintenance planning and execution of proper inspection and maintenance as it's applicable on during the life cycle of the asset. Operational integrity means keep it running, which is appropriate knowledge, experience, manning, and competence, and decision-making data to operate the plant as intended throughout its life cycle. Now, overall, an overview of structural integrity management system, which SIMS, structural integrity, and by definition, structural integrity management system should be implemented to validate, analyze, and update the data more effectively to ensure long-term sustainability and performance. Over structural integrity management system, right, which is adopted based on ISO 19900, ISO 19902, and API RP2 SIMS. And the system, like it's combination of like a documented system, a document which is called like asset integrity management system, where subset is the structural integrity management system, which is built on these ISO and API standards. And similarly, for the buildings or civil side, we have a civil integrity management system, structural integrity management system, electrical integrity management system, pipeline integrity management system. Then it could be pressurized equipment and piping system integrity management system. So there are minimum 9 subsystems which are subset of asset integrity management system. So we provide like a structural integrity management system to ensure that risks associated with the operation of structures are identified and assessed, ensure that structural design are fit for the intended purpose, and engineered to approved standards. Risks are reduced to as low as reasonably practicable. The objective of the structural integrity management system, as I said earlier, we are focusing mainly on the offshore, but it is applicable on the onshore as well. Provide the evaluation of structural damage, and it should cover both above and below seawater inspections, fitness to purpose assessment, any possibility of risk reduction, mitigation planning if there is any kind of damage, and process of decommissioning should also be covered under the same system. I forgot to mention there would be we'll be answering the questions within the break. First part is theoretical background, and then there would be a case study. Up to theoretical part I will cover, and a practical case study would be presented by my colleague Mr. Imran Saeed. And there would be a break, and we will be answering question at 2 stages, one in the middle, one at the end. Please keep typing your questions, and in between also we may try to answer those questions through the question answer window. See, offshore structural life cycle point of view, and if we try to see this, like normal documentation or normal process of life cycle management of subsea structures. See, first is the original design of the subsea structure, then construction and installation and commissioning, then structures are in operational phase. So these are the 3 main steps. At design stage, there are various sets of documents which are mainly applicable to the offshore structures. Like first is the design basis of the structures, then weight control report, like whatever equipment or facilities would be installed on that particular platform. Then there's in-place analysis, pushover or non-linear analysis, fatigue analysis, transportation analysis, load out analysis, lifting analysis. Like when offshore structures are built at basically onshore at the like a jetty area or offshore construction facilities, and then they are moved to the offshore by a barge, and then these jackets and top decks are installed with the help of barges, either by lifting or by load out mechanisms. So these are the various kind of studies are required. The minimum are referred in accordance with API RP2A standard. Then accordingly, detailed designs are done and drawings are prepared, and construction of the structure is done at basically jetty or the area like a yard, which is on the onshore side. And once the decks or the jackets are manufactured, they're moved or load out by a barge, and then offshore installation is done, then hookup and commissioning is done. That is a part of the process. Once structure is in operation, then performing required inspections, and those inspections can be done by the divers, visual inspections by diver or by ROV, and then if any defects are found, those defects are basically repaired maintained for the acceptance level. And there are basically, let's say, cathodic protection anodes. Their depletion rate is basically monitored, and the repair or retrofitting of these anodes is done as life goes on. Then if there is any defect or a flooded member found in the basically structure, that repair is required to be done, then installation of new modules or any new supports as per the requirement or reinforcement of the missing members or any design changes, those are managed as a part of the design changes process. If that is applicable design change, the reassessment, life extension study is done, and then for the life real analysis study, fatigue analysis, pushover analysis, in place analysis, these three analyses are done, and then accordingly decision for the any modification, extra support or any additional member installation, that is done based on these recommendations. Once it is done under the RBI process, what we do normally in the risk-based inspection program, what Velosi used to develop for the future inspections is the review of the previous inspection history, then tag marking over detailed drawings, and development of asset register, which is done based on the general engineering drawings, and then unity check from analysis from the in-place analysis, service life from the fatigue analysis, reserve strength ratio RSR from the pushover analysis. These values are used for the probability of failure analysis, then assessment of consequence of failure, then risk assessment, inspection planning, and these inspection plans are used in the CMS system or ISMS system. Then when we're developing detailed inspection plan, so what to inspect, why to inspect, where to inspect, how to inspect, and when to inspect, these questions are answered as a part of development of the inspection plan. So data acquisition and management, when we are trying to develop the system, normally we need to have the as-built drawing. So our focus is basically now asset in operation. We understand that like it is assumed that the structure is already designed, built, and installed in the field and is being basically supporting the operations by supporting the structure by like the process facilities which are installed on the head of these structures. So what we need to care now is how to plan the inspection for these subsea and above sea structures, and we need to carry out applicable inspections and maintenance activities as those would be applicable. And for that purpose, we would be following or establishing SIMS system, and that is the basis. For that SIMS, for the asset or structure in operation, we need to have as-built drawing, previous analysis report and models, geotechnical data, inspection reports, then meta-ocean data of the field, then equipment layout drawings, details of the modifications carried out till date, existing weight report, and structural design basis. General regulation and industry standards, like for the offshore structure, mainly we are focusing is a APIRP2A. WSD is a planning, designing, and constructing fixed offshore platforms, working stress design. Then APIRP2 SIM, structural integrity management of fixed offshore structures. Then ISO recommended practices, which are ISO 19900 is general requirement for offshore structures. Then ISO 19902 is the petroleum and natural gas industries fixed steel offshore structures. So if we see to SIM index, the title structural integrity management of fixed offshore structures, and this is basically various editions are available. Latest one is September 2020, and what it covers as a normal index, just for reference, people who are not familiar maybe with this standard, the normal scope, the nomenclature or the various terms, the definitions, then structural integrity management overview, which is like a general competency, risk, and limitations of the standard, structural integrity management process, which called like data, evaluation, strategy, program, decommissioning. Then what kind of surveys or inspections are required is chapter number 6. Then damage evaluation is covered under chapter number 7, and structural assessment processes, which are covered under chapter number 8. So it's a easy to follow structure if we try to follow. And similarly, other chapters like chapter number 9 is the assessment of meta ocean data, and then assessment of for fatigue loading, that is chapter number 10, assessment for seismic loading, chapter number 11, and assessment for ice loading if applicable in the areas of like Canada or Russian areas, their temperature is low. Then risk reduction practices which are applicable to structures, chapter number 13, and platform decommissioning is covered under chapter number 14. So these are the total 14 chapters, and then there are figures and appendices A, which can be easily referred while applying this practice or developing your SIM system. So other one like structural integrity management of fixed offshore structures, which is APARP2 SIMS. The purpose of this recommended practice is to provide guidance to owner, operators, and engineers in the implementation and delivery of a process to manage the structural integrity of existing fixed offshore platforms. This process is called structural integrity management system SIM. See, the same system can also be used, similar system for the floating. For example, there could be a FPSO or FSO, and there could be also subsea structures which could be covered under the same system, but we need to add the detail of the required or applicable criteria for these kind of assets. This recommended practice provide guidance for the structural integrity management system of existing fixed offshore structure used for drilling, development, production, and storage of hydrocarbons in offshore areas. Then analysis at design phase of offshore structure, we are giving a little definition like what analysis are required to be conducted. For example, objective of assessments are establish the current stress levels using latest applicable standards, loading, and current in place conditions. Performing non-linear pushover analysis to establish the reserve strength ratio RSR of the structure. Establishing modifications to the loading or structural strengthening if necessary to extend the operating life above the original design life of the structures, which using the fatigue life concept. Then establishing the inspection and mitigation plan for the required life extension of the structures. Now, under in place analysis, which is the first one. So the aim of performing in place analysis is to ensure that offshore structure withstand the load during operation, both gravitational loads and environmental loads, and should be able to survive in extreme weather conditions in the sea. There are the three conditions of in place analysis, namely the operating condition, storm and extreme weather conditions, and pull-out conditions. So all these three conditions should be basically modeled in the while designing the software, designing the structure like SACS or the there is other DNV software is also available which could be used for in-play analysis. Similarly, the following results from the in-place analysis should be checked against the recommendation of APARP2A. For example, member stress ratios, then punching shear check, hydrostatic collapse check, piles capacity and stress ratios, and maximum displacement in the members. The next analysis is the pushover analysis. And the pushover is a static non-linear analysis method where a structure is subjected to gravity loading and a monotonic displacement controlled lateral load pattern, which continuously increase through the elastic and inelastic behavior until an ultimate condition is reached for the structural joint or a member. Pushover analysis is commonly used to evaluate the seismic capacity of existing structures and appears in several recent guidelines for retrofit seismic design. It can also be useful for performance-based design of new building that rely on ductility or redundancies to resist earthquake forces. Objective: of the non-linear pushover analysis is like a non-linear pushover analysis is performed to establish the reserve strength ratios. The RSR is equal to ultimate collapse load divided by 100-year design load. And the acceptance criteria, the factor should be minimum 1.6. The pushover analysis model impact case, you have to completely model the structure, including the bottom, like a jacket part, deck part, and the process part till your helipad area. The pushover analysis model damage case, similarly, it has to be covered fully, and if any damage is there, that has to be modeled and shown in the analysis. Then wave in 0-degree direction, platform just before collapsing. This is like a kind of module taken from the SAC software. Then wave in 45-degree direction, platform just before collapsing. Then this is a 90-degree behavior. And this is a 135-degree behavior when there is an impact of the various loads in the collapsing scenario. Damage case, progressive collapse is also can be seen from the software analysis, and we can see the extreme behavior of the structures through like pushover analysis. So these are like, we are not covering like how this analysis should be done, but we are just showing you when structural engineers are doing this analysis, what kind of pictures and what kind of data is available from the analysis, and which ensure users, operators, like our structure is safe to operate while we are operating it, or we are living on the same living quarters in the sea, and during extreme weather conditions, we can ensure ourselves like we are in the safe hands or safe place. Then fatigue analysis is relatively easy as compared to the in-place analysis. Here, normally we're trying to establish fatigue life of the structures and whether it is more than 50 years, more than 100 years. So fatigue analysis is an aspect of vital importance in establishing the a dimension of offshore structures. This is because of the cyclic nature of the environmental loads, particularly the sea waves and presence of high stress concentrations at the tubular node joints due to current and waves under the sea. In the fatigue analysis, the sea surface is represented by discrete set of waves characterized by period, amplitude, and percentage of occurrence. This the expected fatigue life then is obtained by applying each wave to the structure and totaling the individual effects. What is fatigue? A cyclic loading causing fatigue that with time may result in crack at welded connections of the structural components, joints or members any place. There could be mostly it should be a critical members. Then unless crack propagation is arrested, the crack can eventually lead to member failure at the joint. The propagation of the crack may affect other members at a joint as well. Cracking originally in a secondary brace or like it could be main member or connection, maybe eventually grow into and affect a primary member as well. The result from the fatigue analysis, the remaining fatigue life of a aging fixed offshore structures, then acceptance criteria, joint on the jacket should show fatigue life more than 100 years. And there are the members like where the nodes are having the limitation on the fatigue life. This side, this joint, or you can see here. So a case study, I think detail would be covered by my colleague, Mr. Imran Saeed, but there is a, I think, scope and there is a SIMS content I will cover, and then we will have a break at that stage, and then Mr. Imran Saeed will start. So the case study, what we are saying is the implementation of SIM software for offshore platforms that we have done for a major oil and gas company in this region. And the project scope of work basically was development of structural integrity management system, which is a basically documented system. Then perform risk-based inspection study for the structural platform. As a sample, we are showing you which MDA, JKA, and JKB. These are the name of the platforms. Then perform criticality assessment, develop and develop an inspection plan for mitigating the risk and reducing the cost, and also a future inspection plan, which should be carried out by the client. So quantification of asset for risk-based inspection study, MDA, there were total component like members and joint 382, JKA 2710, it was like a major CPF, then JKB 1306. The total asset covered in MDA, JK and JKB for RBA study are 4398. The following was the deliverable basically as for the project structural integrity management system, SIMS, in line with API RB2 SIMS, then provision and implementation of VAIL-Plant or complete asset integrity management software solution. Following 6 modules were covered, like PIMS for pressurized equipment management system, SIMS for structural integrity management system, PIMS for pipeline integrity management system, EIRMS for electrical instrumentation and rotary management system, then PSV-MS for the pressure safety valve management system, ISMS inspection scheduling management system, and then comprehensive training and hands-on familiarization of VAIL-Plant software was also covered as a part of the scope. Project deliverables, like for this particular like a structural aspect, the tag marking on the drawings, then asset register, criticality and risk ranking, inspection plans, asset passport, inspection drawing, and comprehensive RBI report. So this is the first like a development of structural integrity management manual. So I'm covering this, then my colleague will take over. So development of structural integrity management manual, basically Velosi prepared structural integrity management manual in compliance with API RP2 SIM and company's requirement. SIM manual covered implementation plans and other aspects required to construct the SIMS program, and applicable standards and literature were used as a reference. SIMS manual is applicable to the specific structure of the company. And these are the basically table of content of that particular document. The company asset management framework, SIMS in the life cycle of the aims, then safety case, then performance standards, then technical integrity, then verification parts, adjustment in the continuous improvement, management of change, asset integrity program and plans, which is covering Korean management, inspection, maintenance, and then the safety critical and business critical components. Then there's KPIs. Then this is basically the content list, and then structural integrity management system. It also covered. Also, there's some gap in between. Like we have appendix here, and then we're having the second. So can you comment? Like if I'm missing something here, because this is the first part is I think the same text.
The
right?
same text.
And then this is basically the content list of the documents, right? Yeah. So this is the basically exact content of the document, right? So before we go to the SIMS implementation approach, and my colleague will take over from here, and we can have some question answers, whatever questions are there. No? Okay.
There is one question which we already discussed. For the structure, your question is, if the structure need a periodic inspection, if yes, what is the frequency for the inspection, and how to define the inspection frequency, and how to prepare the scope of work for the inspection.
So I think this will be covering in the next section, and all these questions would be answered, and how we develop inspection plan, what is RBI process, and then the interval is also determined by the same RBI process. So over to you, Mr. Imran Sri, and take over.
Good afternoon, good day to everyone, because we all are based in a different time zone. Somewhere it's afternoon and maybe somewhere it's in the morning or the evening. So now we are in the second part of the presentation, like SIM implementation approach. If you will see this one, like on this flow diagram, like first of all, as part of the risk assessment for the structure, we have to divide the structure into the different components, which will be the primary component, secondary component, and the tertiary component. Then against each component, review of hazards and the failure mode. Then for a criticality assessment, basically we are considering the 3 parameters, the system factor, the probability of the failure, and the consequence. System factor is evaluated based on the redundancy factor, based on the resistance ratio, whereas the probability of the factor that is calculated on the 6 parameters like fatigue analysis, susceptibility to the damage, anomalies, probability of the corrosion, confidence in assessment, utilization factor. So these 6 factors are considered for the probability of the failure assessment. Whereas for the consequence of the failure assessment, the 5 parameters are considered, which includes consequential damage, immediate risk to the life, immediate risk to the environment, immediate risk to the production, cost of the repairs. Then, based on these 12 factors, we calculate the criticality factor, which is basically S, which is the system factor, multiplied by the probability of the failure, that is basically the sum of all 6, and multiplied with the consequence of the failure. Then, based on the criticality ranking, the inspection plan is 12. Inspection plan consists of the inspection frequency, inspection coverage, and the type of the inspection. So that is basically the overall approach. So as part of the study, as a first step, the data collection that includes the steps. Basically, these are the steps as we explained, same like the data information gathering, platform subdivision into the structural components, review of the inspection history, condition data, review of the fatigue analysis, in-place analysis reports and plot plans, development of the asset database, asset register, then the identification of the potential damage mechanism, degradation mechanism, the calculation of the probability of the failure, consequence of the failure, and the system factor. And we have explained in detail in the previous slide for the POF what factor we will consider. Similarly, for the COF, which factor will be considered. Risk ranking and the calculation of the criticality, as explained in the previous slide. The criticality would be the production of the system factor, the product of system factor, probability of the failure, and the consequence of the failure. After the criticality ranking, the next step would be the development of the inspection guideline and the inspection plan. So inspection plan consists of the first step based on the criticality inspection interval or inspection frequency, based on the failure mode, damage mode, type of the inspection, the coverage of the inspection, then selective applicable inspection techniques, and the development of asset passport, or you can say the structure summary report. As part of the SIM study, following documents that have been collected, or you can say that in order to carry out the studies, these documents are required, which consists of, these are basically the minimum documents: structural drawings as built, 3D model if available, inspection reports, details of the modification that are carried out till the date when we are going to perform the assessment, repair reports, replacement and the maintenance records, other. Then as part of the analysis reports and models, if you people remember that when we talked about the SIMS, there were the few documents which we mentioned as part of the design basis, weight control report, in-place analysis, non-linear pushover analysis, and fatigue analysis. These studies which are carried out at the design stage or at any modification, they need to be collected, considered in order to determine the criticality assessment. So second step, after the collection of the data, the structure was divided into the different components. The component will be in the top side member, supply zone member, below supply zone members. The purpose of the, you can say that dividing the structure into the different component is that one, so that against each component we can check from the analysis results, their fatigue, in-place analysis, pushover, then accordingly their criticality and the inspection techniques can be provided in order to ensure the integrity of the whole structure. So if you will see on this one, so after the components that are assigned, marked on a structural drawing, if you will see there, this is a structural drawing where all the vertical members, horizontal members, the nodes, they are identified, they are marked. If you will see this one, there is a methodology. Then, for example, for this horizontal from one beam to another beam, the vertical, similarly the nodes. So all these components are marked on the structural drawing. So against these components, we will check the data from the analysis reports. The fourth step, review of the inspection history, condition data, that is the inspection history data, condition data represents the changes to the characteristics that may occur during the life of the platform. The condition data includes the following: in-service inspection data, for example, underwater inspection, above water inspection, damage evaluation data, corrosion protection data, platform modifications, condition monitoring data, operational incident data. So as part of the RBA study, now we need to consider, as you people mentioned in the flow chart, we mentioned that there are the different parameter factors we need to consider. So first step is in-place analysis as an input to the RBA study. So from the in-place analysis, we will get the unity check value. So unity check value, by definition, it is the ratio of the actual stress over the allowable stress of the component. So based on the unity check values, we have assigned the categories, which may from the low to the high, and we have provided the information into the below table. The unity check for the joints and member is obtained from the in-place analysis report. Unity check values smaller than or equal to 1 satisfy the design criteria of a particular limit state. So this is basically the acceptance criteria for any members of the joint. The unity check value shall be less than the 1. So if the unity check value and the punching ratio, these are detailed, greater than UR 0.9 and PR greater than 0.95, we assign the category high. For the member UC, if it is in between 0.85 to 0.9, and for the joint, unity check is between 0.9 to 0.95, medium category is assigned, and if the unity check is less than 0.85 and for the joint 0.90, then we assigned as a low category. The second step from the pushover analysis that help us in order to determine the system factor, which is basically the redundancy factor, dependent on the importance of the individual component to the overall structure integrity. So if you people remember that one, the acceptance criteria was mentioned like as per API 2A, it's a 1.6. So the system factor, so you will see in the detail into the table. So system factors should be evaluated based on the reserve strength ratio of the platform. Pushover analysis should be performed with intact structure and damaged structure to calculate intact and damaged RSR. In order to calculate the worst damage RSR, damages to the legs of the platform at various points should be simulated in pushover analysis. That my colleague Mr. Rijaz during the first part of the presentation, he explained in detail. So pushover results are required to directly quantify the probability of the structure collapse resulting from a disconnected member. The following should be used to select system factor. So it will be very, for example, less if the reserve strength ratio is less than 1, then we assign the system factor weightage as 1.0. This system factor weightage that will be multiplied with the probability of the failure and the consequence of the failure. If our SR is in between 1 to 1.2, then 0.8. If 1.2, 1.4, 0.6, 1.4 to 1.6, 0.4. And if it is 1.6 or greater, then it will be 0.2. So if you will see this one, the greater RSR value, that will reduce the overall criticality, which means that will increase your confidence on the integrity of your structure, and your inspection frequency would be increased, inspection interval would be increased. The third step, like the fatigue analysis report. So based on the fatigue analysis reports that are used for the probability of the failure assessment, and based on the remaining life results, we have assigned the category. Greater the fatigue life, we will assign the low category. For example, if we have the remaining fatigue life greater than 150 years, we will assign the low. If it is between 60 to 150 years, medium, and less than the 60 years, will be the high category. High category has a more weightage, and ultimately the probability of the failure would be more, whereas the remaining life greater than 150 years, the probability of the failure would be on the lower side, and ultimately the criticality would be on the lower side. After doing all these steps, like dividing such structure into the different components, we prepared a database like the structure components, the description of the component like members, any horizontal nodes, legs, then the structure type, either the component is primary, secondary, then from the inspection history any corrosion damage occur. Then from the different parameters which we observe, the probability of the failure, the consequence of the failure, the system factor from the RSR value, then based on the RSR value, the system factor. So in this way, the database is prepared for the software. As part of the damage mechanism or the degradation mechanism, following are the possible or the potential damage mechanism for the offshore structures, which includes environmental corrosion, crevice corrosion, fatigue, vessel corrosion, installation damage, fabrication flaws, seabed score or the seabed buildup, overload, dropped objects. So these are the potential damage mechanism or the failure modes which are related to the structure integrity. Then, as part of these platform which were covered under this study, the following hazard and failure mode were observed: environmental corrosion, crevice corrosion, and fatigue. Then the criticality was determined from the system by using the equation S into X into Y. X is the probability of the failure, which is taken from the 6 parameter, and Y the consequence of the failure, which is taken basically from the 5 parameter that we have mentioned in our previous slides. So same we are basically mentioned here. So if you will see this one, the criticality ranking, the system factor. So system factor, it is basically redundancy factor dependent on the importance of individual component to the overall structure integrity. The probability of the failure, structure component, there are the 6 parameters which are fatigue analysis, accidental damage, anomalies, likelihood of corrosion, confidence in assessment, utilization factor. So sum of all 6 parameters will give us the overall probability factor. The consequential of failure, there are the 5 parameters that we use as an assessment of the COF, which include the consequential damage, risk to life, risk to environment, risk to production, and cost of repair. So sum of these 5 parameters will give us the overall consequence factor. We basically assigned the weightage against each factor with respect to their ranking from the low, medium, from the low to high. Then the weightage for each factor is assigned. For A to K factor, for the probability and the consequential factor, these weightage are assigned, and these weightage are used in a system to calculate the overall criticality. Once we will get the criticality results, then based on the criticality, the inspection frequency is determined. The inspection frequency that will be based on the criticality, which will be from 1 year, 3 years, 6 years, and then 12 years and for the some component where the low criticality could not be required. So it is basically in accordance with the API-RP2 SIM that defined for the low, medium, and high criticality, which will be 5, 10, and for the low criticality, it will be 12 to 15 years. There are the different type of the inspection that need to be carried out, and as part of this study, we recommended like the GVI, close visual inspection, then the ACFM, CP surveys. So during the operation phase, surveys should be performed in order to safeguard human life, property, protect the environment, and prevent loss of natural resources in accordance with API-RP2 SIM. Based on the calculated criticality ranking, the inspection plan is developed. However, it is recommended that general visual inspection should be carried out for all structure components annually. If protective coating breakdown or excessive corrosion is observed, then thickness measurement should be performed. These are basically based on the GVI for any members where the excessive corrosion observed, then the thickness measurement to be taken for those members in order to check the remaining life. Nodes, joints in the subsea under the high risk shall be inspected. The frequency was defined by using the ACFM to detect any crack initiation. If any new defect are noticed, structure integrity engineer shall assess the defect and further inspection plan shall be initiated based on the recommendation. So as we all are aware that it's not a one-time study, it's a basically complete process. Then again, based on the inspection survey, we need to re-evaluate the criticality assessment. So it's basically after every inspection, the green, you can say the evergreening to be carried out. The purpose of the inspection is to detect or verify the following: indication of the obvious overloading, deteriorating coating system, excessive corrosion, and bent, missing or damaged member of the structure in the splash zone and above water, damage or deterioration to the apprentices and personal safety, escape, and evacuation devices, the performance of the platform underwater CP system. So the applicable inspection techniques used for the condition assessment of the steel structure consist of visual inspection. In the visual inspection, there are two. One is the general visual inspection, that's the annually. Then the closed visual inspection, the MPI, ACFM, CP survey, ultrasonic thickness gauging. For each platform, overall, the structure summary report, that's called the essay report, task force was prepared, which includes the brief description of the assets, criticality metrics, results, conclusion, and the recommendation. So as part of the study, we used our system. So before going to that one, we will take some question. There was one question: have you any experience of using SACS advanced class? Is it comparable to the USFOS? Pros and the cons. Yes, our structure integrity engineer, they have, you can say, vast experience for the using the SACS models. And for any particular query, if you have, you can just send us through the email. Then our engineer will come back to you. Then the next question was there was one question like, why I did not consider the on-bottom stability analysis, ship impact analysis, seismic analysis. So if you people will see this one in our failure mode and the failure identification, vessel collision was considered. Then the seismic analysis, that basically for the structure integrity management system, we are considering the studies and this seismic analysis that were considered for the for your reserve strength ratio, and from those values we have taken the values. So these were the input for the studies and we use that one. Then there was a next question. I see your solution for the structure integrity management is based on the software like SACS for the structure analysis itself. Is DNV software package is compatible with your solution? In the next presentation, we will, in the next part of the presentation, we will present our software. So our software, it is based on the API-RP2 SIM, and we are taking the information from the SACS analysis. based from the second analysis plasticity factor that is considered in order to evaluate the. So once we will give the presentation for the software, you will get the idea about our system. The question is, what is the difference between primary, secondary, and the tertiary component? So basically the difference is like primary components are those components, the failure of any component that will result into the collapse of the overall structure. Second, these are the, you can say, critical members of the structure. Secondary components are those components, for example, whenever they will fail, they will impact on the primary component, and ultimately they will go to the failure of the, you can say this one, the structure collapse. The tertiary components are like the handrails, you can say the minor component, which does not have overall impact on the structural integrity from the collapse point of view. But these primary components, they have like structural legs, nodes, members, they are the primary components. There is a question, is there any recommendation in API RP2 SIM allow us to check the members on the full yield strength, not 0.66? In other ways, we can use AMOD 1.33 in operating case while performing assessment to an old existing structure. So I think you got the answer from our presentation, where based on these values, we are assigning the weightage category. Like if it will be like not in acceptable range, the high category would be assigned, and then ultimately the overall structure criticality would be high, and you have more inspection, less inspection frequency and more inspections. Then we will go now to the our presentation. Then we will come back to again to the question answer session. So we have basically system in the software. We will present the live software. Just give us 1 minute. So we have our VAIL-Plant software. When we click, there are the different modules that are for the topside equipment and piping, pressurized equipment management system, for the structure integrity management system, pipelines, PIMS onshore, for the offshore PIMS offshore, pressure safety, EIRMS. But today our topic is limited to the structure integrity management system. So we will click. Once click, the first screen that will appear, that will be the overall dashboard that represent, which is basically used for the, you can say that the overall, which gives you the summary of overall structures for the management presentation. And on the dashboards, we are mentioning the parameters, like first from the risk or the criticality point of view, then the inspection frequency with respect to the priority, how many components have the frequency at the different topside, splash zone, underwater, then the P inspection and PM activities, how many planned, how many executed, then the distribution of the risk into the risk matrix with respect to POF and the COF. On the left side, we have the hierarchy with respect to the structure, any structure, then we will go like in the structure splash zone, top side, underwater, then in the splash zone, different modules, then with respect to the module, each component, like the jacket, leg, this is the hierarchy. On the left side, we have the like the form view. In the form view, there is the engineering data, RB assessment, inspection plan, coding and result. For similarly, further from the dashboard, when we will click on the risk, we will get the component, detail of the component which are in the risk, high risk category. So from the engineering data, if we will click any component, so the first, that will be the engineering data. On the top, the company hierarchy, like from the hierarchy point of view, company, platform, structure zone, structure, substructure, then the substructure tag, equipment number, type of structure, primary, secondary, component ID, component type, component class. So for these, second, we can go either from this tree, or we have all the structure components here available, and then we can select. Just a minute. So these are the overall in the tags, like the 1000, the total number of the components that are in the system, which are 15,000 components, 14,559 components. So against each component, we can attach the different documents that can be viewed. So if once we click the documents, then we can view these documents in a separate window. So apart from these documents, we can add any document which are related to these components, and we can upload into the system in any like the PFD form, PDF, JPG form. We can also make the integration of the system with any document control system in Vision for any like the structure. One is that we can do the bulk loading. Second, we can also add any edit new trends here. These are the trends where we can see the different trends with respect to the like the structure, like the leak, defects, risk, anomalies that can be seen with respect to the different component, and that can be exported into the Excel also. Second, when we will go to the second is the RBE assessment. So if I will go to the any component, so I will go back to the again presentation so that we will go to the system again. So if you will see this one in the presentation, first is the engineering data for that, like the structure description, elevation, the rows, the axial stress values, then if any CP system installed, the unity check values, operational data, bending stress, shear stress factor. So all these structure values, stress values are written. So same like if you will see this one in the engineering data as we explained through the system also, like the company structure module. Against all the structure data, we are also collecting the inspection history. In the inspection history, like these are the inspection history, general visual, failure record, replacement. In the inspection history, for example, from the general visual inspection, GVI surveys, the module, the position, any anomaly observed, then how much percentage covered, what was the remarks. Then the ultrasonic thickness gauging, if any ultrasonic thickness is carried out against any members, then their frequencies, thickness values, and then it will be compared with respect to the nominal thickness and the corrosion rate metal losses calculated. If the multiple inspection records are available, then CAT can be presented in a graphical form. For the, you can say that component which are under the CP protected, their record is mentioned here, the CP protection, the criteria. In the inspection history, like the failure records, that failure records are mentioned, documented into the failure record tab. And similarly, if any replacement carried out, that replacement would be recorded and documented into the replacement status. So in the probability of the failure assessment, before going to the software page, I will just go to the presentation, then we will again going back to the software. Like in the POF, system will calculate these factors like fatigue analysis, accidental damage, anomalies, corrosion risk, confidence assessment, design utilization factor, then the overall the probability of the failure, the system factor is multiplied. Next step, if you will see this one, this is in the fatigue analysis, as we mentioned earlier, system is considering the remaining life, then based on the remaining life, there is a weightage for this factor. For the accidental damage, based on the type, if susceptible to the dropped object and impact, the high, if susceptible to the dropped object or impact, medium, and susceptibility neither dropped object nor impact, then it will be the low. And whereas in the anomalies, three parameters are considered. One is the crack. If the crack or the through wall defect greater than d/10, then the high weightage is assigned. If the pitting corrosion are d/10, or you can say that impact is d/20, then the medium. If the coating loss and the impact is greater than d/20, then the low. From the corrosion risk assessment, as the structure is divided into the primary into the three parts, like the splash zone, subsea, and the above splash zone or top side. So the members are the component which are in the splash zone, high chances of the corrosion, which are in the subsea, medium, which are in the at the above splash zone top side. The low risk susceptibility to the corrosion. Confidence assessment, like based on the previous inspection record, if any close visual inspection CP survey has been carried out, NDT technician carried out. So based on these in past inspection, the confidence in the assessment is checked and the weightage is assigned. In the design utilization factors, based on these one, system will check the unity check values punching ratio. Then based on that one, system will calculate the design utilization. This screenshot is for the consequence of the failure damage from the system. For the COF, system will consider the following parameter: consequential damage, immediate risk to the life, environment, cost of repair, immediate risk to the production. Then based on that one, system will calculate the overall COF. Then at the bottom, if you will see this one, overall POF, overall COF, SPC life, and then system will calculate the overall criticality. This is the detail for the consequential of failure factor. The questionnaires which we are used, for example, total remover or hauling or tearing, high risk category, major damage, buckling or large deformation, then it will also be the high consequential damage. If the minor damage, localized denting or scraping, medium, total remover or hauling or tearing, high, major damage, buckling or large deformation, medium, minor damage, local, low. Then from the consequence of the failure assessment, particularly for the immediate risk to the life, these questionnaires are considered for the type of the platform, either it is accommodation platform, then in the accommodation platform for all the component, either at all the top side, splash zone, subsea splash zone, their risk categories assigned for the top side and splash zone high, for the subsea medium. Either it is a permanently manned, then based on the permanently manned with respect to the topside structure, subsea, tower, bridge landing, the risk category is assigned, whereas for the unmanned, for the different all component, the immediate risk to the life is low is assigned. So these are the different questionnaires that are used in order to determine the immediate risk to the life. For the environment, based on the product which is at the platform, or the oil, gas, fuel, inhabited, drilling mud, the high immediate risk to environment, these are the utility platform, utility services, medium, and other content as a low. From the production point of view, with respect to the like the size of the platform, from the top side facility, processing facility, for example, if it is, there are the different categories. Based on that one, the immediate risk to the production that was assigned from the low to the high. The cost of the repair, we have the different set of the questionnaire with respect to the repair that was carried out at different component of the structure, which are in the subsea, splash zone, top side, and then the repair type, either extensive, local, or slight. Then based on that one, the risk category was assigned. For example, for subsea extensive, it would be high. For the subsea slight, medium, and topside slight, low, topside extensive as a medium. So these are the different like set of the questionnaires that are used in order to determine the cost of repair as part of the COF. The criticality ranking from the system, these are the like overall result, like the POF factors, COF factor, then the overall criticality. System will give the summary. From the inspection history, like from the thickness measurement record, system will calculate the, if any member thickness calculated, then base thickness of data recorded, then based on that one, system will calculate the metal loss remaining along the corrosion rate, then the inspection results as we explained. Then the system will prepare the inspection plan as inspection reference plan, like the type of the different inspection that would be carried out, close visual, general visual, ultrasonic thickness, with respect to criticality, their inspection interval, and when the next inspection to be carried out. System will also give the the logistic requirement, which logistic requirement like the resources, equipment, the people are required in order to carry out the inspections. Then the inspections, type of the inspection, they are marked on the like structure drawing with respect to the different member nodes, like what type of the inspection to be carried out. The overall dashboard as we presented as part of the study. These are the findings which we these are not the same but mandate. The platform is relatively new platform. The RS value was considered as 0.4. Like some studies were not carried out that we have highlighted. According to the visual inspection report, minor anomalies were observed. Minor corrosion criticality was in between medium and low. According to the drop set test result, CP protection is adequate for the platform. The platform is divided into the protection and the accommodation, and RSR value, reserve strength ratio value of 1.24 was taken from the pushover analysis of the protection platform. The old platform is refurbished and reinstated, hence fatigue analysis is not available. The risk category for 54 component is medium due to the anomalies found in the inspection like the work pack. The accommodation platform is more critical according to the in-place and seismic analysis report. So UC value, so you will also see that there was a one question that where the seismic analysis. So we are basically considering the seismic analysis as part of our assessment. So the UC that are basically used for the UC value checking. So UC value for 41 component is greater than 0.9 as per pushover analysis. According to the drop set results, CP is adequate for all the platform. The platform is divided into protection and race service platform. RSR value of 0.9 was considered. For 107 component critical which are underwater, the criticality is very high, and also the CP values were found to be less than the acceptance criteria, which is 850 to 1100 millivolt, signifying the protection is not adequate in the undersea zone. The risk category for the 73 component is high due to the UC value greater than 0.8 found in place and seismic analysis. Also, major anomalies that bends in legs were observed in some components. As per the inspection plan, recommendation was provided like the GVI, CVI, UTG, ACFM, MPI to be carried out, and the components were marked where the UTG, ACFM, or MPI to be carried out different nodes. Risk levels of each asset can be lowered significantly by performing all the recommended inspection, because inspection will enhance the confidence, and then you will check as part of the reassessment the further condition. The sample drawings where the different type of the inspection as part of the recommendation that were marked. The asset passport summary was prepared, generated. So now we will go to the system. So this is the dashboard for the structure as we explained, and in the presentation, the dashboard represents the risk, inspection frequency, PM activities, POF, and the COF. On the left side, the hierarchy from platform, then in the platform splash zone, top side underwater, then in the splash zone, different component, top side and underwater. In the form view, we have the engineering data, RV assessment, inspection plan. So for any component, when we click, so these are different so on the top side, the hierarchy, as we mentioned, then at the bottom, the engineering data, there's the structure description, elevation, operational status, the diameter, wall thickness, for the particular, we selected one component like the conductor section, the corrosion allowance, the design life, service start, unity check values. On the top, we can see the documents which are related to that component. We can also add the component, the drawings, as we mentioned earlier. Then in the RV assessment, like from the probability of the failure, these are the factors: fatigue analysis, corrosion risk, accidental damage, confidence assessment, anomalies, design ratio. Then system will calculate the probability overall, the pre-OF system factor. So here, basically with respect to the remaining life fatigue life, we will select from the accidental damage based on the susceptibility, either dropped object, impact, or any single or no one. Then the anomalies, the D by the type of the impact, size of impact, the corrosion risk based on the component where it's present, confidence assessment, UVC value. The COF assessment system will calculate based on these parameters. The COF, then the risk matrix, the overall risk matrix of the components for this component. So it belongs into this one, the green category. So these are the for this system, we are using the the 6x6. We can also use the 5x5, but for this, what I am showing, it's 6x6. The probability and the consequence of the failure, then system will overall risk for that component. On the left side, you will see the system factor value for the component, overall POF, COF, criticality ranking, and the inspection frequency. In the inspection recording, history recording, like the different type of the inspections that have been carried out, that would be recorded here, like the GBI, CBI, UTG, that would be recorded here with respect to EML points. Then the inspection plan as a part of the risk assessment regarding the inspection plan is generated from the system. For example, for this component only this GBI. So based on the different type of like if I will go to any other component, so different type of the inspections that are given for the components. So these are with respect to the criticality assessment. Then the inspection results. These are the inspection results that can be viewed from the system. So based on the recording, system will calculate the metal loss, the remaining life, corrosion rate, and the allowances. From the system, these are in the form view, same. We can also review these data into the list view form. Then there are the reports, different reports that are built into the system and that can be generated from the system, like a summary report, criticality report. So with respect to the different platform, we can, like for which component we can require, we can, for example, any component we can just put and we can generate the report from the system. So these are the built-in report, and if you can say this one, the custom, we have also the custom query. Based on the custom query, we can also generate the different report. So we have to select basically any, if I will select, then based on that one, system will create the report. So in this way, system will create the report, any one which we want to require. There are the custom query. Then in the reference document, we can attach the different asset integrity management system, standard operating procedure, and other. Then we will go back. This is basically because for the software, we also provided another webinar, and in future we will also conduct the webinar for the software. So that's all. Now we will go to the question and answer, because then there are the different questions which we already basically from the answered already. This one, what can we do repair method in dolphin pile product? What are the standards for the SIM for chemical manufacturing plants, especially handling corrosive chemical like chlorine, acids? Because today we basically mentioned for the offshore. In the offshore, we mentioned like the API 2A, 2 SIM, ISO 19000. So ISA 19900, the series, that's also applicable for the onshore structure. Then in the onshore structure, there are the other the structure 2C. And yes, this table, these are whatever we have mentioned in the presentation. They are also for the aged platforms. Is VAIL can get input from the SACs regarding the member stress and UR value in the form of direct importing data from the SAC analysis. Basically from the SACs analysis, we will take the information, then we will put into the software templates. So there is no direct integration. We will use the data from the SACs. We will run the SACs, and from the SACs, whatever the output that will come, that we will use as an input into the system. There was one question: if platform designed based on the API 2A structure inspected using the normal program, first the call to use a RP2 SIM, what are the benefits? So the benefits are based on the criticality, you can identify your components, the critical component. Then on those critical component, with respect to the criticality, you can perform the inspections. So it will enhance your confidence. Is the platform helipad is considered for this study or have to carry it out separately? No, basically we will consider under the same risk assessment approach, SIMS approach. There was one question that do your training cover the APA certification and exam, AP, RP2, SIMS, structure integrity, management of the fixed offshore structure? What are the requirements for the training, certification exam? Can it be conducted online? Yes, we are conducting online. You can contact with our, you can send us an emails. We will coordinate with you and we will provide you the training program when the session will be arranged and we have the people. And is there any qualitative way to quickly identify the criticality of the component? The idea is to avoid any structural calculation. So from the presentation, you can see you have noticed that there are the various factors which are used to identify the criticality. And the criticality would be like from the corrosion point of view, the supply zone component, they are high critical as compared to the upside. So similarly, based on the verticalized and your unity check values, you can identify. So these are the basically different parameters on which you can quickly check from your design basis reports. So that's all. Thank you very much, gentlemen. So any question which we did not answer, you can send us and we will reply.